is a multi-phase flow regime that occurs in pipelines and risers. Slug flow forms when gas coalesce into bullet-shaped, diameter-spanning Taylor bubbles. Now between these Taylor bubbles are liquid slugs. Now these liquid slugs travel at speeds in excess of 30 meters per second, inducing severe wear and tear on the system, as well as disrupting production by flooding surface separators. Now, a common method to combat this is the adjustment of a production valve, aka a choke valve. And what this does is, by closing it partially, you introduce back pressure to the system. And this back pressure reduces the velocity of these slugs, thus reducing the damage they cause. What's needed is a control method that can make these valve adjustments autonomously. Therefore, you can mitigate slug flow as well as increase production. Now, the method of control of our focus is PID. It stands for proportional integral derivative. And how this works is the system, through the use of sensors, monitors where it needs to be versus where it is. This is called the magnitude of error, set point versus process value. Now it takes that magnitude of error, and after you properly adjust for the gain values, you implement it into the algorithm and it will yield an output signal. This output signal, in our case, will tell our valve to open or close. But in order to control a valve, you need a valve that is in fact controllable. Our team designed 3 valves, the Mark I, the Mark II, and the Mark III. Mark I and II are side-mounted crossbar designs. The Mark III is a vertically mounted inline design. They all use linear actuators with position feedback, letting us know the valve position at all times. They are wired through a microcontroller. The microcontroller is a wonderful piece of equipment that bridges the gap between the computer and the physical environment. Sensors, motors, name it, it has it. Now for convenience, we designed, programmed, and implemented a graphic user interface through MATLAB. This ensured that any future data collection, data exportation, or PID control adjustments was just a mouse click away.
All right, so in order to do this, we had to build 2 models. The first model here, this small one that you see, this one was actually built in the summer of 2017, and it was made to just analyze slug flow. What we decided to do was to build on that concept, and we wanted to see if we could implement a control to actually help prevent or mitigate, like Derek was saying, the effects of slug flow. So this model right here is, this model right here is, it's 3 foot, it's a small model. Yeah, you can see it up here. With a 1 gallon per minute water pump on it, and an air pump that's regulated by 0 to 40 SCFH regulator. It's 3 foot tall, roughly 6 foot by 3 foot wide. It's a small model. So in order to do that, we wanted to also test and see if the same control will work on a larger model. So what we did was we built the pilot model, which is this large model here. It's 28 feet tall. It's actually outside for after the presentation. It's 28 feet tall, 12 foot by 25 foot footprint on it. And at the top of it, we actually have the same kind of valve up at the top to regulate the pressures inside. On the left side, you can see the clear pipe, that's 2-inch PVC pipe, and at the base of it, we have the manifold, and it's built with a 15 gallon per minute water pump on it and an air injection. Now along the side of the PVC pipe on the riser, there's 3 pressure regulators, and all these pressure regulators are actually wired back to the control module, which is at the bottom in the little doghouse. And by wiring it to this control module, the microcontroller, we can actually hook it to a computer and get real live data of while the model's running that we could compare against the CFD.
To better understand the physics of the fluid dynamics behind the slug flow phenomenon, we ran almost 500 hours of CFD simulations. Geometries for both models were created using Fusion 360, and then the meshing was done using ISOM. Due to the immense computational load for simulations on models this size, instead of using a laptop, we actually used the supercomputing systems available at LSU, and our team is the first petroleum students to ever do so at an undergrad level. Going into this, we wanted to run at least 2 simulations minimum for each model so that we could use a coarse and then a refined mesh in the hopes of comparing the 2 and getting grid independent results. Right here you can see a phase contour animation for the bench scale model. And you can see we get pretty good slugging effect in the pipe. For this model we used a laminar model and it was only stable for about 10 seconds of flow time. Here's a side-by-side comparison of the Taylor bubbles between this model you see here and the simulation. You can see it did a really good job of predicting the size of the bubbles. In the experimental model, they were about 10 to 11 inches on average, and the simulation kicked them out at 10.8. So it's pretty dead on. Moving on to pilot, here's another phase contour animation. This one's about halfway up that big riser. Want to point out that these animations are 2D partitions we made so we could see inside the pipe, but all the simulations were run in 3D. And you can see again, this one has a lot more stable results, but this one was turbulent, so we ran it with a K-epsilon model. Some big delay on this one. There it is. These are pressure and velocity readings at the top transducer in the pilot model. You can see we get these good strong signatures that show the velocity spikes whenever the pressure drops out in between each slug. So between the two, as far as simulation goes, this one provided a lot more stable results. And all in all, we've got about 100, 120 gigs of data that we're still waiting through to compare, and it's going to be really helpful in the future creating and using predictive control.
All right, so before we can even start about talking about PID, generally you want to get some idea of the system dynamics. One way we can do that is what's called a bump test. What we're going to do, the graph on your left is actually the control valve position, the graph on your right is riser base pressure. And this is actually taken from the bench scale model. It would look very similar if you were to compare it to the pilot scale graph results as well. So what you do in a bump test is you actually bump the control variable and look at the response of the process variable, in this case the riser base pressure. And this is done at a steady state using just water. We want to see how quickly the process variable actually responds to the bump. What you see is there's actually not a one-to-one correlation in bumping the control variable and the response of the process variable. So this tells me that there's hysteresis in the system that we need to be mindful of when we're tuning a PID controller. Also, around about 19% valve position, you see the pressure actually spikes. Now we need to be very careful not to overshoot into this almost closed region, because what's going to happen is we could actually make the system worse by doing this. So we don't want to have the pressure rise and release rapidly due to our controller always overshooting, right? Make matters even worse, about 100 to 30%, we have virtually no control with our gate valve design. So just one of the things that happen. This is the uncontrolled slug flow pressure signals. That left is the top, right is the bottom. What you see is it tends to oscillate at plus or minus 1 to 2 psi. Okay, so whenever you look at having a set point for a PID controller, if you're going to try to offset these pressure oscillations, the gains need to be fairly aggressive. Otherwise, it's going to get to a set point and it's going to ignore the natural oscillations of the slug flow. Okay, so we talked a bit earlier about different means of control, and one of them is actually static control, where we crank down the choke valve position. And the idea is that if we raise the pressure in the system, we can decreases the flow rate, but it's going to decrease the velocity of the liquid slugs. If we could do that, then we actually decrease the momentum of these slugs, which ends up being good because then we can reduce the hammering that could go on with these liquid slugs, right? But what you see is we actually, when we do this, at least in our model, that it exaggerated the pressure oscillations. So this tells me that we're actually going to, it's going to have its own set of natural vibrations that are actually going to be worse because of these pressure oscillations. So if we're going to have a good PID controller, what we need to do is we need to have a set point that decreases the momentum of these slugs, but we don't increase the exaggeration of these pressure oscillations. We can do those two things. Our controller is in fact successful. Now, to the fun part, the actual PID control. So this is the PID control for the bench scale model. Vertical line shows you the initiation of the controller, and the horizontal line is the set point of the controller. For the PID of the bench scale model, it's actually 1.2 psi. What you see is it didn't actually exaggerate these pressure oscillations from the natural frequency. Looking over to the left, at least just by looking, you can see that it almost looks the same. In fact, it even almost pulled them up a little bit closer to the line. So just by looking at it, you're like, wow, not too bad. Those two large humps that you see is actually overshooting. And if you look at the top of the graph, We even used a bit of a derivative gain, and still, because of that closed region I talked about, you still had that little bit of overshooting that still occurred. To no surprise, the PID of the pilot model looks pretty similar, so there's no suspense going to be built up there. We actually had the set point about 25 psi on this one, and again, it doesn't look like it exaggerated as bad as, say, a static control. Now, using terms like it looks like, it appears, that's not very scientific, right? That's not, everybody's gonna be like, just your supposition, who knows? So let's actually look and see through what's called a discrete Fourier transform. We're gonna look at the fundamental frequencies of the slug flow and look at the magnitude of those frequencies. And it's separated by the top being the bench and the bottom being the pilot scale. To the left is your static case. In other words, after we had set it and the exaggerated oscillations, we use those data points. And then to the right is our PID controlled case. What you're going to see is actually for both cases, we were able to reduce the magnitude of these frequencies, especially the higher frequency ones. Why is that important? Lower frequency, lower magnitude means lower energy, right? So we're actually able to say with the data to back it up that we are actually controlling slug flow positively, the way we wanted to do it. One thing I do want to point out with the PID controlled for the pilot scale, bottom right, is what you see is a little bit higher magnitude on the lower frequencies. We actually included the overshooting portions of it, which would contribute to a higher magnitude in your lower frequency zones.
For this project, we delivered control valves, a bench model, a pilot model, simulation methods, GUI, and 2 peer-reviewed conference papers, as well as proof of concept for PID control.
And then we want to thank Dr. Michael Malisoff at the LSU Mathematics Department. He actually was the one that brought this problem to our attention. The Kraft and Hawkins Petroleum Department, they've just, of course, they've helped us, taught us, but not only that, they've been very generous with us as well. Dr. Richard Hughes in the Campanile Charity Chair has helped to donate to fund our models. The NSF actually funded the RU that kicked it off last summer, so we want to thank them. And the Center for Computation and Technology for letting us use those Supermic resources. And, of course, our advisor, Dr. Mag Tiagi. And that's it. We'd love to take any questions that you have of us.
Would you stay and do another senior design?
We wanted to show this
we
off
gotta
real quick,
actually,
too.
yeah, if y'all want to see
Okay.
pilot model. You can see the slugs actually form in the riser over here on the side. If you come around to this side, you can see them better. Yeah. You can actually see the tailor bubbles with the slugs being pushed.
When you see it running outside on the pilot model, you'll see how fast